Welcome everyone to the last session of the day, to our invited talk. It's my pleasure. I'm very happy to introduce Zeina Ariola. She has received her PhD in 1992 from Harvard, and since then has been at the University of Oregon, where she has made numerous contributions in mainly in the area of foundations of programming languages. So I won't go into detail, I'll keep this brief, but I just wanted to mention, as many of you know, she is also the founder and longtime organizer of the Oregon Programming Languages Seminar, and she has received the Distinguished Service Award from ACM's SIG plan for this work. So I'll stop there, and it's my pleasure to leave the floor to you, and she will talk about duality in action.
Today, I want to share with you how logic improved our understanding of programs and their implementation. I will start with the question of what it means for a claim to be true. We will then express logic as a dialogue in terms of two disagreeing parties. And this will lead to a symmetric language in which computation is expressed in terms of interaction. This is work done in collaboration with my previous PhD students and with Simon Peyton-Jones. The correspondence between logic and languages goes back to more than half a century ago. And we have the most known correspondence is between natural deduction and lambda calculus, in which a proposition can be seen as a type and a proof as a program. That correspondence can also be extended to second-order quantification, which corresponds to generics and modules. And it also includes classical logic, which can be made to correspond to control flow effects. According to this correspondence, the ex falso Quote-Levet corresponds to aborting a program. Peirce's law corresponds to the call with current continuation, and the double negation elimination to Felizen C control operator. Moreover, the embedding of classical logic into intuitionistic logic can be seen as a common compilation transformation known as CPS. However, let's ask the question, what does it mean for a claim to be true? Let's look at the skeleton of a proof of the theorem that there exist two irrational numbers, x and y, such that x to the power y is rational. The proof proceeds by cases based on the fact that a number is rational or irrational. In both cases, we support the claim. So the proof is done. However, we can ask which values of x and y satisfy the theorem. We are given a choice, but we do not know really how to pick the right one. Of course, we might not be so curious to know which are the witnesses in this case. However, if you are a parent, and I'm sure you would like to know if your son or daughter is a witness of the Drinker theorem. In both cases, the problem is the use of the law of excluded middle, which says that either a claim is true or is false. However, this is based on an omniscient notion of proof of truth, as if we are able as human to prove or know everything. So what we need is a way to provide evidence for the truth of the formula. So we need to explain why a proposition is true, and that this evidence can be based or formulated based on the formula, the shape of the formula. So for example, if I need to prove A and B, what kind of evidence do I have to provide? Well, I have to provide evidence for A and evidence for B. For disjunction, I will need to provide evidence for either A or B, and evidence for an existential, I will need to provide a specific number along with the evidence that the property holds on that number. And I would, at this point, thank you, Paul Downen, for the beautiful drawings that you will see. He's the one that drew them. So the situation so far is that a proof of an existential needs evidence. But what about the proof that a claim is false? Intuitionistic logic does not allow you, does not let you talk directly about falsehood, but we can ask, is the negation of that formula true? So we need to look at how negation is expressed. Evidence for not A is a demonstration that evidence for A generates a contradiction. So there is no obligation to provide a specific counterexample for falsehood. One only needs to show that the counterexample cannot fail to exist. So it seems that the intuitionistic treatment of falsehood sounds very similar to the approach of classical truth. So this scenario now can be depicted as a solitary sage hidden somewhere in the mountains trying to prove a theorem, a claim, prove that a formula is true. So if the sage is able to give us the evidence, then we can verify it. But what if the sage is silent? What does it mean? Does it mean that the formula is false? Or does it mean that the sage needs more time? So what we need is a devil advocate that argue for the other side. So we imagine that the sage can come down from the mountain, become an academic, and now he argues for the truth of a proposition. Then we have the skeptic that instead argue for the falsehood of their claim. And the truth is discovered through a debate of the two parties, with the skeptic asking questions and the sage providing some answers. Okay, but who goes first? If they start talking Italian style, nothing, I mean, it will not be possible to understand. So we need to introduce some order. We can think of a positive burden of proof, according to which is the sage that has to provide evidence of A's truth. Okay, what kind of evidence? Well, it's the same evidence that we have seen in intuitionistic logic. So if the sage has to convince the skeptic that A or B is true, he can provide the evidence for A. If he has to convince that the existential is true, he can provide a witness plus the proof that property holds on that witness. Okay, what does the skeptic do in this case? The skeptic is there to refute all the evidence that the sage is providing. So he keeps arguing for falsehood, and but doesn't provide anything constructive. He just say, for example, in the case of conjunction, he argues A or B is false because it's impossible for A or B to be true. So he rejects all the evidence that the sage provides. In case that he has to prove that the existential is false, he reacts by saying, whatever evidence you give me, the number plus the proof of P of n is never true. Okay? If it were true, we will have a contradiction. What about the negative burden of proof? At this point is the same. The skeptic then needs to do some work and must provide evidence for A's falsehood. So in case that A or B, the skeptic has to provide evidence for both A and B that are false. And for all quantifier, we say that's false. He has to provide a specific counterexample plus the proof that the property on the specific counterexample is false. What does the sage do in this case? So the sage is the one that has to argue the truth. However, in this case, he just reacts to the evidence that the skeptic provides. So he says A or B is true because they cannot be both false. The for all formula is true because that the property is never false for any n. Okay, so it argues with all the evidence that the skeptic provides. What about negation? We have the negative negation, right, that the intuitionistic logic has, is the skeptic that has to provide evidence that not A is false. How does he do that? By providing a concrete evidence that A is true. What does the sage do in this case? Argues that not A is true because there is no way that you could prove that A is true. But we can also see a new negation, a positive negation, in which is the sage that has to convince this skeptic. So the sage, in case of minus A, is saying minus A is true. And here is a concrete evidence, okay, which consists in the proof that A is false. And the skeptic reacts to whatever the sage is saying, and he replies, minus A is false because there is no way you could prove that A is false. Okay, so we arrive at a more nuanced library of connectives. We have the positive connectives and the negative connectives. And with these finer connectives, we are able to give a constructive interpretation of the Morgan laws. Okay, so now let's revisit our excluded middle law. Then we can think about it with a positive mindset. Okay? According to the positive mindset, is the sage that has to provide evidence. So it starts by saying not A is true, and we hope that the skeptic doesn't say anything. But the skeptic comes back and say, no, not A is false. But now the skeptic has to provide the evidence that that is false, and that evidence includes the evidence that A is true. Okay, so now the sage goes back in time and say, oh, I'm sorry, actually, not A is true because A is true. Okay, and at this point, the skeptic cannot say anything. However, we can also have an interpretation of the excluded middle with a negative mindset, okay, in which the sage doesn't have to construct any evidence. Okay? He just says that A bar not A is true because they cannot be both false at the same time. And with that thought, the skeptic cannot build any counter argument. Okay? And so the claim is true. Now, let's have a look at how this logic as a dialogue can lead to a model of computation. We will work with sequence, in which we have a bunch of assumptions on the left-hand side of the turnstile and another set of assumptions on the right-hand side. The way to read this sequence is that the conjunction of the assumption implies the disjunction of the conclusions. We can now have a judgment that represent truth. So if I have empty assumptions and the formula in focus means that the formula is true, but we can also have a judgment that represent falsehood. And we have a judgment, empty assumption, empty conclusion, that means contradiction. But the interesting thing is that we can now have, for each judgment, we can have a corresponding syntactic object in the language. So for example, a proof that a formula is true will correspond to a producer of values of type A. Instead, falsehood is captured by a consumer of values of type A. Contradiction, instead, corresponds to an executable command in which we have a producer that produces information and a consumer that is waiting for that information, and they interact. Of course, we can work with open producer-consumer commands. Then the assumption on the left-hand side will type free variables, and the conclusions on the right-hand side types continuations or output channels. You can think of the producer as the sage, the consumer as the skeptic, and the command as the dialogue between the sage and the skeptic. So you can see the producer as giving an answer, the consumer as the one that asks the questions. However, we can also give different other, let's say, interpretations. You can see the producer as the term and the consumer as the context or the continuation. And the command then corresponds to putting the term in the context. Or you can see the producer as a module that hides information, or a consumer as the one that is polymorphic with respect to the information. Or the producer can be finite and the consumer can be infinite. Okay? In this case, the could also be that the consumer is finite and the producer is infinite, but we can have that duality. Okay, so now let's try to give a computational interpretation of the positive burden of proof. That corresponds to building data, in the sense that constructed positive evidence corresponds to construct values of a data type. For example, the right rules of the sum type. Okay. What do I say? If I have evidence for A, then how do I build an evidence of A plus sum B? By injecting V into the left disjunct, or I can inject it into the right disjunct. How do I build evidence of a tensor with a pair? By joining the two terms that witness A and B. Analogously for the existential is a pair with the witness and then the term witnessing the truth of the formula. Then how do we represent the skeptic? The skeptic is the one that reacts on whatever information the sage provides that corresponds to do the pattern matching. So for example, the skeptic for the A, sum B, will just be the one that if it receives a proof that A is true, then it gives a contradiction represented by the command C1. If I receive a proof that B is true, then I produce another contradiction represented by the command C2. Analogously, for the tensor, the skeptic will receive proofs A and B, proof of A and B. What does it do? Say, no, cannot be, contradiction. The same for the existential. And this corresponds to the elimination rules of lambda calculus. What about negative burden of proof? Well, constructed negative evidence corresponds to constructing co-values of a co-data type. How do I construct evidence of A with B? Well, I just package up the evidence that A is false, and then I inject it in the left component. Or if I have evidence that B is false, that evidence is called F, I inject it in the right component. And for the bar, I need to have evidence that both A and B are false, and I package them together. The same way for the for all quantification, okay, I package together the witness and the proof that B with that witness is false. What does the sage do in this case? It does co-pattern matching on the shape of all possible evidence. So the sage for A with B can be seen as an object. I'm an object and I'm waiting for the consumer to either ask me the first component or the second component. Okay. If you ask me for the first component, then I execute the C1 command, which is a witness that A cannot be false. And analogously, if I need to prove that B cannot be false, then I execute C2, which is the witness of that contradiction. Instead, how do I show that A bar B is true? Okay, well, I'm waiting for the proofs that A and B are false, right? And then I give a contradiction. Okay. So these objects, they pattern match on the request that the consumer is providing. What about the negation? Well, we have the negative negation, which the skeptic evidence contains specific evidence in favor of A. And we see the evidence represented by V. And in this case, the sage is the one that responds by showing that any evidence of the form not X leads to a contradiction. And the positive negation becomes a data type. The sage evidence in favor of minus A contains specific evidence against A. That is the context, the consumer E, okay, that is wrapped up in a new data structure. What does the skeptic do in this case? Responds by showing that any evidence that the sage provides leads to a contradiction, represented by the command C. But so far, we have seen the pattern matching, we have pattern matching constructs and co-pattern matching. Okay. However, in practical programming languages, we're not forced to always pattern match on the shape of a value. So what is the analog of a let expression in our dual language? Well, we really need to extend it with a generic consumer, right, where I'm just waiting for any X. Okay? And then that X is a proof of a claim A, and then I show a contradiction. So this rule can be read as, if assuming that A is true leads to contradiction, then A is false. Dualizing the mu tilde I have a generic mu, okay, where I'm not forced to pattern match on the consumer. I just give a generic name. And this can be read as, if assuming A false leads to a contradiction, then A is true. With this in mind, now we can give a program, a computation interpretation of our law of excluded middle. So the positive law of excluded middle capture the context in alpha, and it's clear that there is a control flow, a change in control flow, by the fact that the continuation alpha is referred to twice. The first time with the injection to the second disjunct, and then a second time we invoke the same continuation by giving back the proof of A. We can also give a computation interpretation of the negative law of excluded middle, expressed by the display term that uses co-patterns, where now is the sage that is waiting for a proof of A and a proof of not A, but the proof of not A includes the evidence called X of A, and therefore I form the contradiction. Okay, so how does this dialogue is explained? Is explained using the beta rules, and the dialogue happened when the producer and the producer gives some information, and the consumer is ready to accept that information. So for the positive law, I see that the producer is the one that construct the data, the consumer is the one waiting, and then we bind the variable to the evidence provided. For the negative, instead is the consumer that builds the data, and the producer is waiting for the data, and now there is the dialogue by matching the right evidence to the variable. But there is also other laws that express the fact that the deconstruction and construction do not gain any information if they are done one after the other. And we have the positive eta law that are expressed in terms of a generic covariable, and the eta law for the negative that are expressed in terms of a generic variable. Why is that the case? Because for a positive connective is the consumer who does the destructure. Okay, so that's why we just named the consumer alpha. And for the tensor, for example, it says that I'm a consumer and I'm waiting for a pair. I take the pair apart and then I rebuild it. Well, that does not add any information. Instead, the eta law for the negative is on the term side, because it's the term side that does the deconstruction. So for example, for the wave, I am an object, I'm waiting for a message to ask for the first component. And then what I do, I just repackage the message and send it to X. And if he sends me a message for the second component, I repackage again that request and send it to X. Okay? That is work that is useless. Notice how the eta law for the positive connected are better captured in this dual setting than in lambda calculus, because in lambda calculus are expressed in terms of this context, but in lambda calculus the context is at the meta level. But now the question that we can ask is, what are those contexts? Any context? Well, it means that at this point we need to talk about evaluation. So if I have a function called f applied to 1 plus 1, we can ask, is 1 + 1 done before or after the call? And in a call by value setting, then we need to evaluate 1 + 1 first. So it means that in call by value, favor the producer of information. It doesn't matter if I don't need that information, but the producer has precedence. In call by name, instead, we follow the consumer, the use of information. Okay. So if I have a command in which the producer sends 1 to a channel alpha, and the consumer sends 2 to the channel alpha, then in the call by value setting, I will see 1 on alpha, and in the call by name, I will see 2 on channel alpha. How do we express these different evaluation strategies in our dual setting? We can do that by insisting that we only substitute values and co-values. So we don't substitute general terms, only values and co-values. And of course, their definition depends on the language. For example, in call by value, any context is a co-value. And instead, I have a more restricted notion of value. Like, for example, a tuple is a value only when both components are values. And instead, the terms of negative type, they are values, they're objects that are there waiting for the request. In call by name, instead, is the dual. Any value is a, any term is a value. Okay, any term. And I see a typo that should be a small v. So anyway, in call by name, any term is a value. Okay, but then I have a more restricted notion of co-value. For example, the request of the first component of a pair. Okay, I cannot just request the first component and then not needing the first component. So I only have a co-value or evaluation context when I have pi1 and then a co-value, and the same for pi2. Instead, the context that are waiting for a value, they are directly co-value. So like the mu tilde waiting for a sum type. This notion of value and co-value can be extended to capture call by need and also co-need, which is the door. Okay, so far we have seen these connectives, predefined connectives and or negation. Okay, but what if we want to define new connectives? What do we need in our language in order to define our connective of positive or negative polarity? Okay, well, the connective of positive polarity can be given by listing the patterns of constructions. Okay, this is what's happened with algebraic data types. So in the sequent setting, we make clear that the formula in focus will be separated by the rest of the conclusion, separated by a vertical bar. What about the codata types? Well, we can just list the pattern of destruction. So we can imagine defining the A with B in this case, where I say first, and notice now the formula in focus is to the left, indicating that I am waiting for a pair. And the A to the right-hand side stands for a consumer. So in order to build a message for A with B, I need first a context or a continuation of type A, okay? And then I tag that request with first. But you could define this definition in Java using an interface. However, we also have other connectives like minus and par that are not definable right now in current programming languages because they require additional continuations. Like, for example, the par is I need to have two continuation of type A and B. And the minus, I need a continuation. I have one output, which is the current output that I built, but then I also have to have a continuation around of type A. Interesting, also the function type doesn't have to be a predefined type, can be defined using CoData, because again, CoData, you specify how to build the observations. In case of function, in the CoData, I will specify the shape of the call stack. And what is that shape? I have a term V of type A, that's the argument, and then I need a context of type B, where to send the result. So the CoData is a common denominator between functional and object-oriented languages. Use in why functional programming matters motivates the utility of functional programming through its excellence in compositionality, which is reached through demand-driven programming, which in Haskell is realized with lazy evaluation. However, I don't think that is lazy evaluation what we should strive for, but the concept that is at the heart of demand-driven programming is CoData, because it gives you the support or the capability to yield control to the consumer independently of the language being strict or lazy. And in fact, OCaml has been extended with CoData, and we are currently working in extending Haskell. Having a language with both data and CoData can provide an approach to the expression problem. We can then represent also pre and post conditions with this data and CoData. For example, data type indices allow you to constrain how values are constructed. Okay, so I can check that the representation of a program is ill-typed. And the same thing is with CoData, where I can use indexes to constrain how values are destructed. For example, I can represent a socket protocol, and where I can insist that before sending a message, the user has to connect. So for example, in this, if I just allocate a new socket, which will start with raw, now I bind it, and now the socket becomes bound, and now I start to use it, but I cannot because the send requires my socket to be live. And that's not the situation, so that will be ill-typed. So far, I have described this dual language, and I want to continue with the presentation of how logic has also helped us in solving some specific problems in programming. For example, let's consider call by name lambda calculus, and the question is how to combine extensionality, weak head reduction, and computational effects. According to extensionality, lambda x omega x is equal to omega, where omega is a program that loops forever. But now we have that the program that ends immediately is the same as one that loops. how do I then solve the problem? Well, instead of doing weak head reduction, we go with head reduction. But the issue is, how do I do it efficiently and with avoiding renaming? But now we have to remember that a function is not constructed. Okay? It is a distractor of the calling context. Okay, so I see my lambda is just a distractor. But now let's remember that in languages with let expression, I pattern match, but I can translate the pattern matching by substituting I can just give a name, right, to that variable, to that value, v, and then substituting the first component of that value for x and the second component. So in order to proceed, I don't really need the v to reduce to a pair. So we can apply the same idea in our example. Suppose I have my lambda and I embed it in a context that called TP, which represents the top level. Okay, how can I proceed? Well, I proceed with C, and now for X, I substitute the first argument of the top level, and for beta, I substitute the second argument. The same thing that I did in the previous example. We then have my lambda expression that I run it at the top level, but now I can just select the break the top level apart. So now I have omega applied to the argument of store in the top level. Then I'm in an Absa machine, I push the argument on top of the stack, and now I have omega at the end. Okay, so by seeing the lambda as a distractor, I can make sense of head reduction. But also it helps in restoring confluence of functional extensionality in the presence of control effects. So here I have my lambda. Then if I do eta reduction, that would be the same as abort 5. But I could also execute the reduction rule corresponding to the abort. So I have lambda x and only abort 5. How can I then bring the two together? Abort lambda x, abort 5, which is just represented right, more explicitly using the argument and the continuation. Then I give a name to that pair and continue with abort 5, and now beta becomes the second component of my call stack. Then I can just abort 5, I delete the return component, I just return alpha, and then another eta on mu, and that returns to abort 5. In other way, I can bring together the right-hand side term to the left-hand side. Okay, another thing that wasn't clear, at least to me, is how to understand loops in programs and proofs. We have our canonical examples of inductive type, NAT, and co-inductive type, string. And we know how to work with inductive types, and we can write our plus function that induct right, on the first argument. So we convince ourselves that that is well defined. Why? Because the structure of the first argument decreases. So it doesn't really matter if the part in blue gets bigger. Okay? Doesn't matter, we found something that is decreasing. Okay, now let's see some example of streams. How do I define a stream starting from a given starting point x, f of x, and continue to iterate? I can define the function based on the observations. Of course, I cannot build it constructively, and so I define it based on the request. If you're asking me for the head, then I apply f to x and I'm done. But if you ask me for the tail, then the message gets resolved, okay? But the accumulator gets bigger because the accumulator will be representing f applied to x. So why is this productive, this definition? Does it make sense? Yes, it is inductive in the context. Okay? What gets smaller is the context, and sooner or later we will reach the base case represented by the head. We can define analogously the map function that maps a function to a string, and the same, how does the do I convince myself that this makes sense? Because it's the context that gets smaller. Okay, but now I want to prove something about the positive type. So for example, I want to prove something of A sum B. What does it mean? Well, I just prove the property for all possible shapes of value of that type. And in this case, we are lucky because we only have two possible shapes. Of course, if we are dealing with math, we cannot write the proof by cases, but we know that we can just assume that the property holds for a generic y, right? And then we prove the property for successor of the same y. So induction follows the structure of values of the producers. But now I want to prove maybe something of the width type. Okay. That is the what is constructed is the consumer, are the observations. So I can do a proof by cases on all possible observations of that type. And as before, I'm lucky because I only have two observations. Either you request the first component or you request the second component. Then what about the string? I have an infinite number of observations, so I cannot do a proof by co-cases, but analogously to induction, I assume that my property holds for a generic string y, and then I prove that the property holds for the tail y. So now the request gets bigger. So co-induction follows the structure of context. Now I want to say a few words about how logic improve our understanding of compilation. We know that in lambda calculus, an application, okay, is represented like in the left-hand side. And the problem with this representation is just that the next regex is down, but it takes time to find it because I have to continue searching till I reach the end. Instead of in the sequence calculus, the main action is moved to the top of the program. But this is also similar to what's happening in continuation passing style and static single assignment. However, this static single assignment is an imperative representation. Instead, the sequence is a good fit between functional or effectful languages. Moreover, the function calls in the sequence are more concrete because concrete than CPS, and that allows better optimizations, especially for Haskell, where the user can specify optimization using rewriting rules directly on the source syntax. Another issue that we were trying to solve is how to represent sharing of code in the representation. The sharing of code is known as a join point or fee node in SSA. We can think of representing that join point in terms of a function. Like, for example, in this case, okay, I have my case expression, and then I invoke in both cases, I join into function j. But of course, I don't want to implement really this join point using the function is as good as an abstraction, but as an implementation, functions are very expensive. So what the compiler does in this case is recognizing that j is a special function because it's tail call. So instead of generating a function call, the compiler will generate a jump to j. Okay? But there the compiler applies other optimizations. So now it tries to move the straight context 3+ inside all the branches of my case expression. And now you see that j is not tail call any longer. So the compiler cannot generate a jump instruction because I go to j, but then have to come back. So I ruin with this optimization, I ruin the possibility for the compiler to generate fast code. So how can I do then that optimization? Well, we got the idea directly from the sequent, because if you write this expression in the sequent calculus, then the context is not moved inside the case expression the same way that is depicted in the first example, but the strict context is moved inside the join point directly. This means that I can now generate fast code both before and after optimizations. The current intermediate language of Haskell has these join points, and I repeat again, the idea came directly from the sequent calculus. So far, we have talked about strict languages and lazy languages. So, but let's see the advantages or disadvantages of these languages. Lazy languages do not have sums. Okay, why is that? Because remember the eta axiom for positive are expressed in terms of alpha, and I said that we only substitute evaluation context or co-value for alpha. Okay, so then the eta axiom does not apply to all context as in call by value. Or then maybe we should just forget about lazy languages and stick to strict languages, eager languages. But eager languages do not have products. The same problem, the eta law, is expressed in terms of a generic x, and I can only substitute values for x. In call by name, any term is a value, so things work out, but in call by value, it doesn't. But now polarity comes to rescue, and polarity say, pick the connectives, or the connectives, sorry, are given the best case scenario. Positive types are called by value, and negative type are called by name. Okay, you don't have to pick one strategy for the entire language. The strategy can be dictated by the type. But then how do I embed call by name in call by value? Because I still want to compile Haskell right down to this polarized language. Well, we know that we need shifts to preserve the notion of a value, course, I need to have a way to delay a producer. How do I embed call by value into call by name? Well, I need to have a way to delay the consumer. And with this shift, downshift, and upshift, then we can encode call by value and call by name. No problem. Then what about call by need? Call by need is about sharing. So within, how do we preserve the sharing? Then we know the sharing is preserved by data constructors, and sharing is ended by co-data object, like a lambda. Any computation inside the lambda is duplicated. So we can extend polarity with a new kind, star, and then we add 4 more shifts, okay, between star and the old one. The shift between call by need and call by value are data types, and so that they preserve the sharing. And the shift between call by need and call by name are co-data types. And so now we can encode in this polarized setting in which we have a finite number of connectives and these different shifts, and we can encode call by need, some type, and call by need functions. Not only that, we can encode all user-defined data and co-data types. Can be encoded faithfully using just a finite number of primitive connectives and shifts. And we encode actually call by need and also the dual of call by need. Another question that we were asking is how to compile function call efficiently. We know functional languages, functions take only one argument at a time. It's nice, it's recurring, it's very nice, but from implementation point of view, is very costly. So then if I have a function of int, arrow int, arrow int, and say, oh, I can just package up those 2 ints in a tuple, okay, and then pass the tuple at once. And if I have a function g on the left-hand side here, well, I could translate it to function f. And it seems that I will not get into trouble. But what if I have a function like age of x that then throws up an error? Then that behavior is not captured by the other type. Okay, so I cannot just translate, do anchoring, okay, at will in languages like OCaml and Haskell. Okay, so then the compiler has to figure out, to do an analysis to figure out the arity, meaning how many arguments does the function take before it does serious work. If I only see the type int, arrow int, arrow int, I don't have any clue. All 4 functions have that type. But I could say the function f1 and f2, safely say that those functions take 2 arguments. But instead, function f3 and f4, if I want to observe the allocating a tank for z, or if I'm in a call by value language, expensive x would be expensive. So I cannot say f3 and f4 have arity 2. So the question is, how can I express the arity in a type? Do I have to invent a new type? Interestingly, polarized logic gives us the answer another time. The primitive function type must be a call by name function type, because the type fuse together. So if a function int, arrow int is a truly negative type, I will say that all those functions have arity 2. Okay? So I can express the arity using the negative function type. And this notion we are currently extending the intermediate language of Haskell with this notion of primitive function. Okay, I can conclude what we have done. We have analyzed many facets of duality when the is the producer that is finite, the consumer that is infinite, or for negative type is the other way around, is the producer that is infinite and is the consumer that is finite. We have translated idea from logic to computation and got inspiration from logic to better understand program behavior and implement program more efficiently. However, I will say that what we learn from all this work is that the best strategy in the end is to embrace diversity and to work together with the opponent in the search of truth, but work together. Okay, thank you, and I can answer any questions.
Thank you very much. Okay, we can thank the speaker. So we do have time for questions. You can raise your hand or ask a question in the chat. Let's see. Okay, there's let's start with a question in the chat. So the question is, what is the mu operator?
The mu is just a way to give a name to the context. Okay, it's similar mu alpha, if you want, is similar to call CC. I name the context alpha.
Okay. Other questions? Maybe I can ask, so you talked about object-oriented versus functional. Can you say a bit more about that? It was, or maybe I just...
because, I mean, to me, before doing this work, I was seeing the two completely isolated, right? But now with this concept of data and codata, I see a possibility of defining a common language in which I can translate object-oriented, because object-oriented languages, they only have codata, okay, and no data. Instead, functional languages, they favor data with one codata. But at the end, I think that, like what I said at the end of the talk, the best way is to embrace both. We should not fight, oh, object-oriented is better or functional programming is better. I think in the end, we need both. And for me, the main concept of object-oriented is this concept of, I'm an object and I'm reacting to messages. Okay? And we don't have that concept in functional programming. So at the end, we need both. That would be my result. The same way for laziness and eager, right?
Right.
So there is no perfect world. Okay? We will always find a disadvantage of one or the other. Mm-hmm. So it's much better to find a way to embrace both.
Mm-hmm. Okay. Oh, here's another question. What about efficient implementation of arrays?
Oh, well, maybe, I mean, that array could be represented through, I don't know, a pointer. And again, I think that that concept can be represented in the type. So I could imagine saying, oh, well, I pass this array either by value, by reference. That information should be represented in the type. So yeah, data representation should be part of the type as well. So I don't know if I answered that question.
Yeah, that was a question in the chat. Okay, we have a raised hand, Herman. Do I need to unmute?
I already did it, but it is not working. Let me try again.
Okay.
No, I cannot unmute him for some reason.
Can you?
Oh, you have to unmute yourself, Herman. I already give you the permission to do it. Otherwise, I will make you co-host and then you will be
Yes.
able to do whatever. Okay, now you are co-host, so you should be able to unmute yourself, Herman. Herman, are you there? Can you write in the chat or something? Okay, we'll just him.
Hello?
Yes.
Okay.
Sorry. Yeah, so it took me some time to get everything done. So sorry, when talking about iteration over streams, you said that the definition is correct because the context gets smaller. I remember you said that. Now,
Yeah.
traditionally, people say that stream functions are correct because they are productive or guarded or something like that. Is that
Yeah.
is that kind of the same notion? Or
Yes, yes. Now I think that yeah, it's the same notion. Yes.
Okay.
Yeah. So it's the accumulator. The point is that the accumulator can get bigger, but it doesn't matter, right?
Okay.
I make progress and I give back something. Yeah, I think
Okay,
that is similar. But to me, I like induction, so I just like to dualize it. And
Okay. Thank you. Yeah.
yeah.
Any other questions? Okay, if not, I'll give another few seconds if anybody has any questions. Okay, if not, we can thank the speaker again. Yep, thanks very much.
Thank you. Thank you.
And Alejandro, did you want to say anything, or are there social rooms after this, or not? Or we end for today?
The social rooms are open 24 hours, so you can join at any time. But this is the end of the day, so this is the last session for today. So you can continue in the social rooms at Clouder.
Okay, thank you.
Okay. Thank you. Thank you,
Mhm.
everyone. Maybe thanks, Alejandro. Thanks, everybody, for inviting me. This was, and sorry, the talk was too long. Sorry. I cut it some here and there, but yes. Okay.
Well, it's very interesting, though. Thank you.
Thank you. Bye.
Bye.
Bye, thank you.